to explain to our colleagues why. Yes. Yeah. Is it recording? The recording has started. So today's lesson is on statistical modeling. There are two parts to our lesson today. There's regression and inference. So it's possible that we are going to make use of the whiteboard in today's class. As we approach the latter part of the entire program, we are going to also make use of breakout rooms because we are going to be doing, there's a project day, okay? I think it is the 9th lecture dedicated to projects, and we are going to do those projects collaboratively. I wish that we had a bigger house, but we are okay with what we have, provided we all have our computers and we are ready to replicate what is on the screen. Doing data science cannot be achieved by just watching, the screen. It's about replicating the code that are going to be sent to us or that we are going to see displayed on the screen. That makes a whole lot of difference. So we are looking at regression and inference. Our outline for today is, though brief, but loaded. First, we will look at linear regression, which helps us to model relationship between variables, albeit relationships that are linear. Because there are also regression models that are non-linear. For instance, we have polynomial regression. Don't forget that our course is titled Data Science Fundamentals. So whatever we are, undergoing at this first instance of interaction between us and you is just to lay a foundation which can be built upon. Okay. So having said that, when we have done with, explaining and introducing linear regression, we will now begin to do analysis of the concept. At that point, we'll need to talk about interpretation of results. When you have a model and you now feed it with data and you do your analysis, results will be produced. And then we'll be looking at, items in the results such as the coefficient, the parameters that will be estimated. We'll explain the concept of p-values and we see it in its implementation. And then we'll look at R-squared. The third thing that we are doing is hypothesis testing and confidence intervals, which helps us to put quantity in relationships. And this is actually research as it were, trying to either consolidate on the existing status quo or revising the default state of things. So there we'll be talking about null hypothesis and alternative hypothesis. And then we'll be looking at the range where we can accommodate, the hypothesis and then the boundaries. So that's where confidence intervals will come in place. Lastly, we'll talk about residual analysis and model evaluation, which ensures model validity. As simple as this is a typical process that will be replicated in other models. Today it is regression, tomorrow it could be another model, okay? So next week we'll be looking at machine learning, which is another very exciting topic. So this is the outline for today. We are not so much in a hurry to cover everything, but we will take our time, yes. Somehow we might have to speed up at certain times because we want to do demonstration of the coding, which at this point now is becoming more important in a sense. So what is regression analysis? It is a statistical technique used to model relationships between variables, which means that it is not the only statistical technique. There are several. Regression is one of them. And as I said earlier, it is used for modeling relationships. Okay. And we are now saying that what we are looking at today is regression and inference. But our outline says linear regression. So at the general level, we are going to say regression analysis is a statistical technique used to model relationship between variables. But when it is linear regression, as we are going to see later, we will see that it's specifically defined. Moving forward, what are the benefits of regression analysis? It helps us in prediction. It also helps us in explanation and hypothesis testing. So in that second bullet point, we see how we came about covering the curriculum for today. We are going to be doing predictions, we are going to be explaining the results, and then we'll also do hypothesis testing. So as said before, and we are reiterating, the types of regression models that we will cover are linear regression, which models relationship between one dependent variable and one independent variable at the basic level. So when we say linear regression, we can have simple linear regression. So this linear regression you see on the screen, first you can take it as the relationship between dependent and independent variables. But if we now call it simple linear regression, then it will be the relationship between one dependent variable and one independent variable. We are going to demonstrate all of this later. So subsumed in this linear regression is the idea that we are defining relationship between independent and dependent variables on one hand, but we are saying there's a unique type called the simple linear regression, which is one independent variable to one dependent variable. As we go on, we are going to talk about this issue of independence and dependence and relationships. At this point, we're only setting the stage. When you now have many independent variables predicting one dependent variable, which sometimes is referred to as the outcome variable, then we now talk of multiple regression. Lastly, there's logistic regression. This is unlike the other two. Why? Because it helps us to do classification. Later on in this course, we'll talk about classification models, a lot of them. But this logistic regression is a binary classifier where you do true or false, pass or fail, yes or no, good or bad, just true possible values. Permit me to say that we are looking at regression today, but logistic regression does not predict a numerical value. When you use linear regression, it predicts a numerical value. I'm assuming that there are lots of us that are statistics, lecturers. But when we go to the subsequent slides, we'll take our time and explain what we meant by numerical values and then the issue of binary classification. But let's just keep this in mind, that linear regression and multiple regression are used when you are trying to predict a numerical value. But when you are predicting categories, classes, then the kind of regression that you have when it is two classes is the logistic regression. Great. So here is an example of a linear regression equation. In this equation, y, which is the outcome that you seek to find out, this is your dependent variable. Maybe we'll take an example, very basic example. Say you want to model the linear relationship between the study hour of a student. So let me now share whiteboard. I think that's easier for me. So I'll go to virtual whiteboard, and then we can begin to move away from our material, and then we'll return to it later. I hope you can see my screen. Can you see my screen?
Yes.
Okay. Great. So this is how data normally comes. You have a variable x1, let's assume that this variable x1 is the number of hours that the student spends studying. It's just an example. And then here we have our y values. And what we want to predict is the grade of the child. Now, if we are predicting grade and we have just 2 levels, say pass or fail, no, that's 2 levels, then what we are modeling is a logistic regression. But if we are predicting more than 2 levels, we could use other kinds of classifiers. But if we decide to use logistic regression, we'll call that multiple logistic regression. But the example we are looking at now is not classification. We want to predict a value. So we are going to change this grade to the score. Okay? That will be the score in the exam. In that case, let's say the total score is 100, in which case a student can score between 0 and 100. So that's what we meant when we were talking about numerical value. So what we are predicting, which is the outcome, are the scores. So let's assume that we have a student A, and that student reads for 2 hours a day. And then there's a student B who reads for 4 hours a day, and then a student C who reads for 1 hour a day. And we found out that this student that read for 2 hours scored 60% in the exam. The one that read for 4 hours, let's assume scored 66. And then this one that read for 1 hour, let's assume that this scored 51. So looking at this relationship, we can conclude, without even plotting a graph, that as the number of hours changes, for instance, the score also changes as one. Then we can also see that it seemed to us, so if I decide to make this 10 hours a day and this student is so studious, and the student still gets 51, then we can see, because there are only 3, observations, we can say maybe this thing is not really linear. But let's assume that that student scored 81. Then we can conclude that if we plot a graph of x, in this case, x1, if we like, and then y on the vertical axis, it appears to me as you move forward in terms of hours, the score will also move up. So when you are going to plot a line of best fit, it's going to look like a rising graph from left to right. It is not all the points that will fit on the line, of course, but we are just saying that we are going to see this kind of rise. So if you're able to capture this kind of relationship, then we are talking about linear regression, but not just linear regression, but simple linear regression, because we have only one variable. But if we have another variable, say x2, and then this x2 is class attendance, we are looking at how often the student attends the class, then it means that y is now no longer dependent on just one variable, but dependent on multiple variables. I think I heard the sound, which seemed to me as if somebody's raising hands. Yes, Dr. Ademola, go on, please. Dr. Ademola, was it an accidental thing that happened, or you wanted to say something? Okay, maybe it was an accidental thing. Welcome, everybody. We have more people in class. We are still going to do the R demonstration. The meeting is being recorded, so you have access to the recordings. For now, what we are looking at is linear regression. And we are saying that if it is just one variable, then you call that simple linear regression. If you have more than one variable, it now becomes multiple linear regression. So I came here because we said here that this is linear regression equation. And you see that there's one independent variable. Because you have only one independent variable, that's why we said it is the simple linear regression. Where y is the outcome that you seek to get, and x is the variable that predicts. So it's sometimes known as the predictor or feature or independent variable. All those terms refer to x. So x is a variable that changes, y is a variable that changes, but beta naught and beta 1 are your estimates that you need to get. So when you now get beta naught, we call that beta naught cap because it's an estimate, then beta 1 cap. Without going into so much technicalities, I will just tell you that x determines y based on the value of beta 1.
Yes.
So later on, when we are going to check our results and then we are going to explain, we are going to look at the value that is in front of x, which is the coefficient, okay? And we are going to use that as the amount of influence that x has on y. We are going to explain that later. But you see, in every model or in most models, there are levels of uncertainty, which is the noise or the error term. So this is included because you will never have a perfect fit. If you go back to our line of best fit, you will see that even in the example that we used, we try to demonstrate the fact that, yes, we are getting this line of best fit, but some values are falling out of that line. That's where our error term comes in. And we'll still talk more about that. What then is beta naught? Beta naught will be the intercept on the axis. So if I draw this graph, this place where your graph touches the y-axis is our beta naught. It is the intercept. There was beta 1. Beta 1 is when we find the slope. So beta 1 for this simple linear regression is the change in value of y with respect to the change in value of x. Remember that this linear regression that we are talking about at this level is the simple linear regression. If you are not from the background of math, statistics, science, and all that, all you just need to know from this is that the x value determines the value of y. Okay, so for instance, if you invest money in a business and then you now have profits, we are saying that the amount of money that you invest can determine the amount of profit that you are going to come up with. So it happens, in many fields of life. The use case that we have in our demonstration is predicting the price of a house. Let's get interactive. If I want to predict the cost of a house, what are some of the variables that can influence the price of a house? You can unmute yourself and let's hear one or two people tell us some variables that can determine the price of a house. Anybody?
Location.
Exactly. So if we are using only location to predict the price of a house, then we are dealing in simple linear regression. Just one feature. Do we have another person with another feature? Any other characteristic?
The price of building materials.
Okay, good. So we can now say the cost or the type of building, the number of rooms. We have seen location. Now we are saying
let's say structure. The structure,
yeah,
structure of the building.
Brilliant. So now we've seen three variables. Okay, the quality of materials that has been used, the kind of building that it is it just a bungalow, a duplex, or a story building and high rise or an estate. So those are factors. So when you have several of them that have linear relationship, meaning that as one variable rises, the other one rises or drops. Okay, linear relationship is a situation whereby an increase in one variable either leads to an increase in the other variable or a decrease in the other variable. Not when you cannot capture whether it's an increase or decrease. When you can't capture an increase or a decrease, you say it is non-linear. And there are regression models for that. For instance, there's what we call the polynomial regression. I can see Dr. Ademola's hand up. I guess he wants to say something. You want to say something, sir? Or that hand has just been there? Okay. Yes, let's take it. Ademola, are you saying something, sir? Hello? 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 Okay, let's keep going. Let's keep going. Let's keep going. We are already making progress. And I'm glad it's something that some of us are already used to. So, example, case 1, predicting house prices. The second case is analyzing sales trend. So when you're analyzing the trend of sales, you can now start thinking of variables such as number of customers that came, the quantity of goods that they bought, maybe the day of the week, the hour of the day. Those are some variables that can affect the trend of sales, whether it's on the rise or on the drop or it's static. However, once it is a single variable that is influencing our output, they will say that is simple linear regression. If it is beyond one, then you say it is multiple linear regression. The third example here is estimating the revenue from business. All right. But before we begin to look at, implementing it in R, I will go back to my whiteboard and then I will say that if you want to get the equation for multiple linear regression, then you'll be talking about, having your Y equal to your beta naught will always be there. That is the amount of change that happens when no variable is causing a change. What it means is that this world is stochastic, it's always, change. There's nothing that is certain. So without the influence of any of the variables that you are using in your model, there could be a change in the value of Y. That's what the intercept is. Okay. So if we now say we have 5 independent variables, if you have X1, the parameter in front of X1 will be beta 1. If you go for another variable and that variable is another feature that is affecting, then you have beta 2. And we can have it up to beta n. So we can have dot, dot, dot. So it means that we have beta, and the variable we are going to have here will be xn. And then certainly we must add the error term. So this is an example of a multiple linear regression. If it was polynomial regression, what we are going to have would be, instead of x1s, you could have x to the power of 3, okay? And then we can call this beta 1 and all of that. I don't want to delve into this because it's not part of the fundamentals that we're supposed to learn. So how do we distinguish between linear and polynomial? It is the fact that this one is raised to a power that is greater than 1. Notice that these ones don't have power. So in mathematics, when there's no power, we know that the power there is 1. So let's go back to our notes and let's pause at this point and then ask us if we have any questions, any comments, because the real thing in today's class is the hands-on coding. I'm going to ask some of us to share our screens. You will run the code. We will see the problem with your code. That is when learning has taken place. There is no learning when the instructor comes and explains the material. If the participants are unable to replicate the material and apply that knowledge to other, situations, then learning has not taken place. So with that, I'm going to go back to the class and then find out from us if we have questions, comments, contributions, or concerns. Please, let's respond. Did you have questions, Is it okay with what we have done so far? You know, we are looking at regression. We are still going to look at confidence interval. Dr. Yusuf Taiwo, you want to say something? Or is it Professor Yusuf Taiwo? Good evening, ma. I can see you smiling. You have something to say. You can unmute yourself. You are muted. I can see you talking, but I can't hear you. Okay, while we wait for her, Dr. Demola, you want to say something? I see you are muted.
Hello, can you hear me now?
Yes, I can hear you, sir. Yes, sir.
I've been that time, but I'm having you communicating. The other time, my whiteboard was not showing at all.
Your whiteboard, right?
Yeah, I can see it, but there was nothing written on it except Y, X and Y.
Okay,
I don't know why that is happening to me anyway.
Okay, your whiteboard or my whiteboard?
Your whiteboard, let me put it that way.
Yeah. So the whiteboard is white. So until you write something on it, so I will show it again, and then you confirm that you can see what is on it.
Okay.
Can you see?
Not yet.
Aban, can the others see my board? Can you see my screen? Hello, everyone.
Not yet. Not yet. I've not seen it.
Is there somebody who can see my screen?
Yes, we are seeing.
Yes, we are seeing your screen.
What have I written now?
Yes, I can see it now.
Good.
Y is got to beta naught plus
Exactly.
beta 1s1 plus this.
Exactly.
Multiple regression.
Fantastic.
So what we did this before.
Okay, good. Thank you so much. So what we let me just go around it again. What we just did was we said that at the simple level, you have Y and X, giving us, this linear relationship. Then we said when we have more than one X, this is hours of the day spent reading. It's just, artificial data. And then we said this is attendance in class. But don't worry, we'll still demonstrate all of these things as we go on. Thank God that you can now see the screen.
Thank you.
Yeah, so now this is the business part of the lecture. The business part of the lecture is I want us to write this code. Okay? I want you to be the ones running this code on your system. So this is like an exercise. I'm going to explain this whole code, to us. But I want to see if you can replicate this code yourself. So I'm going to leave this screen a few minutes. Okay, or maybe I can run mine. Okay, maybe I should just run mine and hope that you also run yours. So I want to split my board into two. So I'm going to split my board into two. So here I have my R, and here I have my PowerPoint, my presentation. Okay. So I wish that you can also split your screen like that. If you want to know how to split your screen, maybe I should just do a demonstration. I don't know if Prof. Okay, no, I've been the one teaching. So let's do a demonstration. If I want to split this screen, can you see my screen? Can you see my screen? You can see my screen, right?
We are seeing.
Yes, we can. Yeah, we can see it.
Okay, so I'll take my cursor to, this one is minimize. This one is maximize. So once it has done that, it will ask you, how do you want to maximize it? Do you want to have just two panels, or you want 3 panels, or you want 4? Let me take these 3 panels. See what it has done for me. It has given me my Discord channel. It has also given me my PDF and has given me my R code. So I'm going to make this full screen again and show you. What I want is just 2 portions. So if I click on this, I don't want this code. So I want R. So I'll go to R. And R is not giving me full screen. So I can start from R and use R to split into 2. Okay, so I've now split this into two. Whether you were able to split into two or not, you now want to write the code. If you've not written any line of code before and you have R, you are going to learn today. So we go to File. I'm creating a new file. So I'll go to File. I'll do New File. Okay, just like you're opening a new document, maybe a Microsoft Word document. But you need R script. You want R script. When you click on R script, it will create a new note, empty note. But you see, the problem now is that I already have information here. So I can go to this icon here. It says it clears objects from the workspace. It looks like a broom. So if I click on it, it will ask me whether I want to clean up everywhere. I'll say yes. So environment will be clean. I also don't want this. I want a clean slate. So I'll go to this place where I have this, clear console to clear it. And now I have a clean slate. Then I can do Control Z, or I can go to File and do Save As. So I can do Save As. I want to save on my desktop. So I'll go to Desktop. Let me see if I have FSS document. Okay. So I'll go and save this in Professor Lubusoye. I'll go there. Let me see if I created FSS inside Professor Lubusoye. Okay, that's where I'll be keeping my files. So I already have this file hypothesis testing. But no, I want to write this code all over again. So I will give it a file name. I can now call it hypothesis _4 _FSS. You can name it anything. So I will save that. So even though it's a blank file, but you can see that the name of the file is here, hypothesis _FSS.R. The .R means that it's an R file. So I want to split my screen again. So now I've split my screen. And why have I done that? Because I want to see the notes so that I can copy the notes. So here, I don't know if you have done this. I hope you have done it. But since we have recording, we want to build a linear regression model in R. I wish you can just follow me and code and all that. And if I'm able to finish this lecture, that would just be, it would be great for me that at least the participants are actually getting this thing hands-on. So I will say library. Why will I use library? Okay, good. So if you were around last week, we talked about visualization, talked about using graphs and curves and plots and lines and charts to communicate information. And one of the libraries, or the main library we looked at last week, was ggplot2. So if you don't have ggplot2, which is not going to be true, it comes with the R package. What you would have done is you would do install.packages. We'll come back to that if necessary. So I'm going to write library here. And once you start typing, it gives you the option. So what I normally do is when I see it's the option that I need, I click on it. Inside there, I'll write ggplot2. And then I'll click on run. If it produces an output and you get this symbol, this greater than symbol, it means that it has executed this line and it has completed its work. I'm deliberately taking my time today because I desire that on the other side, you are actually also writing this code. This is week 4. As at this week, you are supposed to now, code really. Watching it, which can be temptation, will not, all go well. So please, let's try. So I'll go to line 2, which I'm actually taking from here. I don't actually want you to copy and paste. No, that won't help us today. So when I get here, I'll write library. And inside that library, I'll write DP LYR. This is for manipulating data. So this library will also run. But it now gives me a warning. Sometimes the warning might not be green. When warning is green, it means that it's not a big deal. Okay. When warning is red, that could be a very big deal. So what is this warning that it tells me? It says that I should know that this DPLYR was built under R version 4.33. That's just to say, ensure that you know the version of your R instance. We won't go into that today. When we get to next week's lecture, I will show you how to find out that. I don't want you to learn too many things. So today we are using so far two libraries. What are they? The ggplot2 for plotting the graph, and then the PDPLYR for manipulation. Okay? I hope we are doing well. Now, in terms of data, there are many ways that you can get data. You can create your own data. You can also use someone else's data. But here we want to create artificial data. And that's where simulation comes in. So we want to get simulated data. But because I don't want to forget what I did in the following line, I can then write a comment. If I write anything here, it will be white if it's just text. But if I now put hashtag in front of it, it will change to purple. Why? Because if I run this line of code, it will not be executed, it will not be activated, it will not work. It's just giving myself notes. So why did I say that? Because I want to write here example of simulated data. This is a very good practice when you are doing research. Okay, before you even go to the field, try to generate artificial data and then run, use it in your model and then run an experiment. If you are able to simulate properly, and simulating properly also depends on your understanding of the kind of results that you expect, your understanding of the problem that you are solving. Okay, when you do that, you help yourself with the final result, because the preliminary analysis that you do with simulated data gives you an advantage over somebody who just gets data and then begins to run with it. Now, sometimes you do research and you don't do research alone. You could do research with other people, or you have your research, but somebody else wants to use it. For that person to get the same results as you when you use simulated data sets, you need to set a seed. You need to ensure that when values are picked randomly, that person that wants to replicate your work will pick exactly the same values that you have used. That's the purpose of this next line. So when we say set seed, we are saying that so that someone else will reproduce the exact same result that I have, set my seed as 234. Notice that in this document, what we have is 42. So what I'm going to do is, I'm going to use 234, run the simulation, we'll look at the output, and then compare it to when we use 42. What you are going to notice is that the random values that will be picked will be different. So in summary, when you set seed, the goal is to ensure that someone else who wants to reproduce your simulated data set will pick exactly the same samples. So in line 6, we are not using data that practically exists. We are not using real data. We are using synthetic data, artificial data. We are just creating an abstraction. So what we do is that we want to convert that data set to the form of the normal spreadsheet, or what we call a data frame. So we can now name this anything. I can call it sample. Okay. But in this, our document, we have chosen to call it DF. So I'm going to stick to that DF, which could just be an acronym for data frame. Okay, so you are free to use whatever name there. Okay, you saw that that thing gave me a red. You gave me this red here. Let me just show us that. When I did data frame and I had this, there was this. Let me put a value here. It will show me that there is an error in that line. Okay, because this should not be equal to, it should be a dash. What is in my data frame or what is in DF? DF is not a number. It is not letters that are in DF. What I want to create in DF is like a spreadsheet. So I'll use a function. The function that I'm going to use will be data frame. Okay, so you see it's already given me data frame. In front of that data frame, I will have a bracket. Whenever you write a function, you put a bracket in front of it. So what kind of data frame do I want to create? Notice that what I did there was just to press enter. Once you press enter, it takes it to the next line. And on its own, it forms an indentation. Now, we are doing simple linear regression. One dependent variable and one independent variable. What do we seek to do? We want to get the ages. We want to generate a random sample between age 20 and age 60. And we want 100 values. And we just add this argument, which says replace is true. It's just the default value. So we go on and say there are two variables here. There's age and there's salary. At this point, we are not saying anyone is dependent or independent. So if I go inside there and I write age, I can do less than with dash, and it will still suffice. Then I'll get the sample function. What would the sample function do? It will help us to generate random samples from the numbers 20 to 60, that age range. And we need 100 of them. And then we add our last argument, which is that replace is true. So I don't know if you are writing this along with me, but I'll be very glad if you were doing it. Then that means we are done with our X values. Okay, X now exists. We have created a data set with 100 observations and 100 values under the age column. But the least value, the range of the age will be between 20 and 60. So you put a comma and press enter, and then you take your next variable, which is salary. You do the same thing using the same function sample. But right now, you want the salary to be between 30,000. Remember, notice that I didn't put a comma there. And then you want it to be 120,000 as the maximum. Okay? And then you also want 100 samples so that it be consistent. And then you say replace is equal to true. If I run any line in this place, it will save for me. Let me make this full screen. Let me bring this down so that I can follow very well. So first we loaded ggplot2. We loaded dplyr. We set the seed for reproducibility. We created the data frame. Inside the data frame, we have age and salary. So if we do DF and we print that out, okay? If I want to see what is in DF, this is what is in DF. This is what is in my data frame. I've created a data frame. Why is this giving me this? So let's scroll to the top. So this data frame gives me the age. Yes, go on. Somebody just, hello? Hello? So let me bring this portion down. Hello? 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 Let's go back to our class. Let's find out if there's somebody that is worried. Hello? Hello? Any problem? Okay, if there's a problem, we can always address the problem. So if you have any issues, please let me know. Okay, so now I have the two panels. I want to get feedback. Please help me. Are we okay? So these are the salaries. We will get the data frame later. Are we okay, or do we need help? Is there somebody who is replicating this, or we are all just watching? Hello, class. Hello, class. Hello.
Yeah, we are watching you because personally I'm not on system presently.
But do you understand what we're doing, man?
I'm following you.
We are with you.
Okay, good. Fantastic. Fantastic. So we now have our data frame already created. The next step that we want to undertake is to fit a linear regression model. So I'm going to put my hashtag and I'm going to say fit a linear regression model. This idea is very good. What I'm going to do is at the end of this, I will send this file to you so that for those of you who couldn't code along with me, you have it easy. So how do we fit a linear regression model? We need to use the LM function. So there's a function called the LM function. That is the linear model function. So what do? We create an object, a variable. We can call it anything. For now, we'll call it model. And then we assign that model a value or an expression. What expression? We take the linear model function. This LM is for building linear regression. Then what do we do inside? We identify our dependent variable. So let's talk about this particular example. The way the example is structured, it appears to me that we want age to determine salary. Okay? Age will be in one column, salary will be in the other column. We want to see how age influences salary, which means that salary will be the dependent variable and age will be the independent variable. So we write our dependent variable first, and then we add the tidal symbol. That symbol is before number 1. Okay, before figure 1 on your left. Maybe what I should just do is this. Maybe I should just, there's something I can do. I can say keyboard images is important so that will not discourage some of us from, coding. So if this is our keyboard, here we have our tilde symbol. If this is number 1, number 2, the tilde symbol is by the edge. Okay, good. So let's go on. Let's go. It's here on top of tab, but you have to do control that symbol. I wish you could experiment it. So moving forward, salary is the dependent variable. Age in this one is the independent variable. Yes? Hello? So in this expression, you want to capture two things. You want to capture the variables and then the data. So here you've seen the variables, then you now assign the value of the data. In our own case, our data is TF. It can be anything in your own case. When you run this, what you have done is that you have created a linear model. Okay? A linear model that models the relationship between salary and age. In actual fact, how salary is influenced by age. And then you have built-in data. This data is not real data, but artificial data. On this environment panel, you will see that you have your age, there are integers between 1 and 100, and the first value is 46, and the first individual earns 93,530, and it goes on that way. Okay? So what is the next thing that is in our material? The next thing in our material, which is far one of the most important things that we are going to do today, is to look at the summary statistics. This is like the exploratory data analysis. So by using this summary function on our object, which we call model, we will get the final result. So I can now say summary, like summarizing the model. If I run this line of code, I will get my result. So I'm going to push this up. I'll push this portion up. And then I'll push this to the side so that we can now do interpretation. If you remember, when we were introducing today's lecture, we said that we will now look at how to interpret the results. We'll talk about p-values, and all of that. So let's look at this result. This is the line of code that we have just run. We created a model, a linear regression model that models how age influences salary. And we use simulated data that we call data frame. When we see the results, first thing that is going to tell us is to show us the model specification. So even if you've not seen the code, and what you have is just this output, you can actually say something about this output. What do you see? You see that the function used is linear regression, and the formula or equation is salary depending on age, and the name of our data is data frame. Somebody is trying to join the meeting. All right, good. So we'll go back to our result. So we see here the residuals. And the residuals are now at 5 levels. I don't know if you have seen a box plot before, but even if you have not, it will be good for me to use a box plot to explain that result. It's important. So I will write box plot images. So this is a box plot where you have minimum value, maximum value, lower quartile, which is 25%, median, which is 50%, and the upper quartile. It is that same idea that you will see in the result when it begins to show you the values of the residuals. It gives you the minimum. Don't forget that it's salary that you are predicting. Okay? The minimum, the first quartile, the median, the third quartile, and the maximum. Not the maximum values, but the maximum value in terms of the residuals. Remember that when we were looking at our whiteboard, let me go to the whiteboard. We said that we have a regression model. Wow, our whiteboard is gone. Okay, even if we don't go to our whiteboard, we can go to this material and show you what we are saying. We saw that y is equal to beta naught plus beta 1x plus this residual, this error term. Okay, the smaller this value is, the better. Okay, your prediction becomes better when that value is much smaller. That's what we are seeing here, not the y values. Then when we talk about coefficients, we are talking about beta naught and beta 1. Okay, in our own case, our beta naught is the intercept. And then our beta 1 is our age. Don't forget that salary is what we are predicting, that's why. And age is the predictor, the independent variable, just one independent variable. So if you now come to where we have this result and you now want to interpret it, you will see that in trying to predict our salary, our parameters, our estimators are two. First, intercept, which is beta naught, and age, which is beta 1. With respect to the intercept, we have estimated standard deviation, we have the error value, we have the t-value, and then the probability. This probability is our p-value, and that's the one that matters to us most. And you don't even need to really know the value. You just need to check if it is highlighted as significant. These asterisks first tells you that it's significant and also tells you how significant it is, depending on the levels that you have used for testing. Because you see, we have margins of error, our alpha level, which can be 10%, it can be 5%, it can be 1%, it can even be 0.1. So it is possible for something to be significant at a certain percentage, but not significant at another percentage. I'm trying to say it this way because I reckon that not all of us have background in mathematics or statistics. So if you see that here we have significance code, maximum, this is at 10%. Sorry, this is at 100%, 100. 100 over 100 is 1. 0.1 at 10%. That means you have 90% confidence in your result. You only have 10% margin of error. Okay, let's give 10% of mistakes. Then when it's 0.05, it means that you have 95% confidence and say 5% error margin. If you see a dot in front of the p-value, it means that it is significant at that 0.5. If it is just one asterisk, it's significant at 0.1. If it is double asterisk, it's significant at 0.001. And if it is triple asterisk, it's significant even when you don't give any, error chance. If it is just this, inverted commas, then you know that it's at 0.1. I know this is making sense to us. So if we now look at the H, which is our beta one, this is the estimated standard error. What it means is that, estimated standard deviation. It means that with 303.4 change or variance, or allowing for 2.15.3 level of error, you can have a 1 value raised in salary. I will talk more about this maybe in subsequent, demonstration. But what is significant for you is that you need to know is that by the time you look at this p-value, this p-value is 0.162. When we get to hypothesis testing and all of that, further into confidence interval, we'll come back to this demonstration that I'm showing you. So at 0.162, that is 0.162, which is not up to 1, not more, it is more than 0.1, you are not going to have the kind of significance that you expect. That is why this one that is 2.1, it's to the power of -9. This value is actually 216 divided by 1 billion, because there are 9 zeros in 1 billion. So it's really a small value. So it means that intercept is really contributing to it. Don't forget that this is simulated data. What about when making decisions? Yes, when you now want to make decisions, you also need to now begin to talk about the R-squared, which we'll see in the subsequent notes. I'm not saying much about this for now because we'll go back to the lessons and then we'll flesh this up. What I wanted to do and why I came here was for you to be able to run this and get an output. So let me go back to our note and ask, is there any question at this point before we continue? Let's take a break and ask questions. Did that demonstration make sense? Were you able to replicate it? Can we proceed? 3 questions. Anybody? I just need one person to respond, then we'll go on. Anybody, please. Messi Olugu, Jami Aziz, want to say something? Hello? 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 Okay, let's take 2 minutes break. When we return, we'll go back to our slide and then continue and end the class with demonstration. 2 minutes break. I'll be back. Hello. So I don't know whether you went on break, but I did, and I hope you also did. Dr. Friday Oboba, you are very focused. Are you coding? You are very focused on that material. Is it working for you? It's not working. Can you share your screen? Do you know how to share your screen? Do you know the icon for sharing screen? Should I stop my screen so that I can share, or I should go on? Which one? You are nodding. I don't know. I don't know whether you are saying yes or no. Should I continue? Yes. I should continue. I want to share. Which one? Dr. Friday is not responding.
Yeah, I am. Just continue and follow it.
Okay, great, fantastic. So don't worry, you'll be fine. All right. So what we have done so far is to look at linear regression and then try out an example, and we're able to get, those results. So this was what I was trying to, explain to us. And I said, it's better that we run through the material so that you can get the understanding, and then we'll now go back to the R code. So we now have our summary, the output. In that output, we are supposed to talk about coefficients. So the coefficients are the estimates. They are beta naught and beta 1 in our example, because we are talking about only one independent variable. So beta naught is the intercept on the vertical axis, y-axis, and the slope is beta 1. So if we had more predictors, more x's, we'll have beta 1, beta 2, and so on. Then p-value, okay? So this shows to what extent, okay, is it the effect of a variable on the output? Is it enough? Is age really a determinant of salary? To what level does age influence salary? how much of it can we ascribe to age? When somebody's salary changes, is it really a function of age? And if it's a function of age, is age really contributing that much when you ignore other variables? So we say significance of relationship between variables is what you get in p-value. And then the R-squared is what percentage of variability is explained by the model. The changes that we see in the salary, to what level do we ascribe it to our model? What is it? What percentage of it are we going to say, yes, it is because we are modeled in this way. That's why we are getting this level of change. So an example of an output that can really help us, and I'm going to take my time here so that I can get it. It looks like the output that we had, only that the values are different. Here we have intercept, which is like our beta naught. And here we have age, which is like our beta 1. So we say, when age increases by 1 year, a 1 year increase in age will result in a 1,200 units increase in salary. That's what this says. If it is negative, then you say it's a decrease. So we will still check it in our R code. Then with regards to intercept, the value is 25,000. And this represents the predicted salary when age is not a factor. So when age is equal to 0, remember that when we plotted our graph, we said something like the intercept on the vertical axis. We drew something like this. So let's say this place is age. And let's say this place is salary. And at the end of the day, we have this graph. So this beta naught, that is our intercept, is the salary when age is 0. So if we now have an increase in age from 0 to 1, and then salary now increases here, okay, we are saying a change from 0 to 1 results in a change from this initial level to this other level. Okay, so that's why beta 1 is the slope, otherwise called gradient. Okay, secondary school mathematics. Okay, good. So let's go on to our material. So intercept of 25,000 represent the predicted salary when age is equal to 0. Moving forward, we now want to have an extension. Okay. The good thing about the whiteboard that I've shown us before is that it just helps us so that when we now get to where the note is in our, PDF or our notebook, we will see that we have already mentioned it, and it appears we are hearing it a second time. So multiple linear regression is an extension of simple linear regression because it uses many independent variables. The equation looks like this. You still have your y, which is what you want to predict, but now you have more than one x. Your error term is still there. Your intercept is there, but as many variables that you have will determine the number of coefficients that you are going to, estimate. So we say x1, x2 up to xn are the independent variables, while beta 1, beta 2 to beta n, and they are their respective coefficients. Beta 1 for x1, beta 2 for x2. And that's what you want to, calculate. Let's use that word, estimate. So when do we use multiple linear regression? We use multiple linear regression when we now have more variables and we want to capture, the relationships. Because when one variable influences another, that's simple. But when many variables influence, one output, then that's complex. Okay. Beyond this foundational discussion, at another level, when we are revisiting these things, we will now talk about, the conditions that will make us to use even the linear regression model. but that's not for now. So we also say that we use multiple linear regression because we want to eliminate the problem of bias. We cannot just say there is only age that determines the salary of workers. Okay, there is qualification, there is their, working experience. Okay, so what are we saying? If we want to reduce the bias that is not just one variable, then we introduce several variables, which will now all contribute to the outcome that we seek. Also, if you use multiple linear regression, you are more likely going to have a higher, predictive power. You'll be more accurate. Your precision will be more. Okay, but if you have one independent variable, then you don't use multiple linear regression. Don't just feel that since multiple linear regression seem to be, giving us all these positive features, these very interesting attributes, then let me just use multiple linear regression. No, you use multiple linear regression when you have more than one independent variable. We're only saying that it gives you a better predictive power. So what are instances when you use multiple linear regression? These are use cases and they are inexhaustive. You cannot just restrict yourself to these examples here. So let's speak to these examples. First of all, in business and finance, you can use multiple linear regression for forecasting sales. You want to predict revenue based on marketing, spend, customer behavior, and seasonality. So what you are predicting is revenue, but you are looking at how much you spent in the market, you are looking at behavior of customers, and you're looking at seasonality. So there are three independent variables predicting the outcome, which is revenue. Then also in risk analysis. Okay, so in this instance, you are estimating loan default, the probability that an individual will default in payment of loan. But you are basing that on certain features. One, the income of the person, the credit score, maybe the credit profile of that person, and the amount of debt that the person has. So again, we have three features, three variables, three independent variables, estimating, whether an individual, the probability that an individual will default. So in healthcare and medicine, you can use linear regression for predicting the likelihood that an individual will have a particular disease. For instance, predicting heart disease risk based on the following features. One, the body mass index. Two, the blood pressure, and then the cholesterol. I'm pretty confident that a lot of us on this platform will understand this very well, because once you get to a certain age in life, this disease now becomes something that you need to consider. So just as a passing comment, please know your blood pressure and cholesterol level. Okay, so beyond that, we can also, use multiple linear regression. Yes, we are saying multiple linear regression because you see that at each example, we are given more than one predictor, that is more than one independent variable. So in estimating the cost of, medical care, okay, we want to estimate hospital expenses. That's our why. We want to base that on, one, the age of the patient, the kind of condition that the person is facing, and the kind of treatment that the fellow is undergoing. In marketing and advertising, we can do customer engagement prediction. That is, estimating customer retention. We want to see how, customers are being retained by a business. And we are looking at variables such as how often the website is being visited, how many people are clicking on the emails and then, interacting with them, and how interactive the adverts are. I can tell you for free that for me, some of those adverts are really stress to me. You are doing serious work, that's what I call it. And then an advert comes. I don't waste time to just, cancel those adverts. I don't know if you have that kind of habit as I have. I don't know whether it's good or bad. Then in marketing and advertising continued, you can, assess effectiveness of an advert. How is this advert performing? Based on how much is spent on it, the kind of groups that are being, targeted, and the style of campaign that is used in advertising. In real estate and housing, which is the example that we looked at, the example that we used before, we can estimate the price of a house based on, you remember we said location. We also talked about the size, how big the house is, then the number of rooms and the age of the house. So you see that multiple linear regression is really used. So you're already doing data science. It's just that we are still doing the fundamentals, but really I think we are making progress. So we come here, similar to the same example that we had before. This time around, I might not write the entire code. Salary, age, experience, education. Okay, no problem. So we want to fit a multiple linear regression model in R. This is going to be our assignment. Okay. What do I mean by assignment? Something that you can practice during the week. Okay, it will be good for you to have something to practice this week, because next week's lecture is machine learning, and machine learning is a bit tough. Let me use that word. Okay. So, but I believe that you can easily see that the first part of this code is similar to what we did before. Okay. But what we did was salary and age. So we've added two more independent variables. Experience. We are sampling experience from 1 year experience to 40 years experience. And we are sampling education, that this person has spent 12 years in school. That means has finished primary school and secondary school, minimum. And then people who have 20 years, apparently who have gone to higher tertiary institutions and all of that. But I think in this group, we don't have somebody who has really, read up to the zenith of education. So what I'm just saying in essence is that this looks like the previous one. And if I just take all of this, for instance, and I go to my R, and then I come here, and then I put, say, hashtag. Let me put hashtags. And then I copy that. I've copied it. Okay? So this is what was missing that I couldn't see there. I would have said, let me write this again myself, but no. So now I want to stick to the set seed. Remember the set seed for reproducibility. I will run that. Then data frame is created. I'll create this model now. It's still a linear model, but now it's not salary and age alone. It is salary, which is the dependent variable, okay, which is, dependent on age plus experience plus education, and the data frame is still the same new one. So what I want to do is I want to distinguish the two data frames. So I'm going to call this DF2, okay, deliberately, so that it will be different from the previous one. And then I'll come here and call this place DF2 also. Let me bring this thing down, and then let's run it again from the top. So here I have set seed. Let me clean up this place. Good. So I set seed, I run that, I create data frame that is DF2, I model, and then I get summary. Okay. So you will see that if we go here, remember the description I gave you. We're still going back to our material. But here you see that by just looking at this, you will see that these three variables are not significant at 0.1. What do I mean by that? Let's return to our material and go on so that we can capture that ourselves. So what we have done is we have tried to run this code and we have our results. Remember that our interpretations are to get the coefficients, okay, which show the impact of age, experience, and education on salary. To also get the p-values that determine statistical significance, and then the R squared, which gives us the amount of variance that results from the model. So if I go to our output and we want to, just make comments on the results, we see here that we have the formula, the linear model, then we have the distribution of the residuals, and then looking at the coefficients, we can see that education actually sort of has a negative, in terms of the standard error, a negative value. But here is where you look at, okay? So a 1 year increase in education will result in an increase in the salary by 1,052.12, ignoring experience and age. And then if you come here, you will see that an additional 1 year rise in experience will result in 251.31 increase in salary. You can see that education plays a lot. That's why these values are negative. That's a discussion in another setting. So I was saying that I wasn't going to say much when we're looking at the simple linear, but now we have somewhat to say when we now move to the multiple linear regression. These results here, we'll still see more of them, okay? So we can go back and just relax a bit and see that we have covered part of what we intended to do today. Our goal was linear regression and hypothesis testing. I'm going to pause here and ask, is there really a question so far? Because hypothesis testing is something that we are familiar with. So let me go to the class and check if there are comments, questions, concerns. Okay, so we are back. We are 14 in class. Yes, who wants to say something?
Hello.
Yes, doctor. Thank you, sir.
Okay, sir. I want to find out what is the function of error time, because that was not actually taken care of in the code.
That's
like
true.
when you have the linear regression, y is equal to beta naught plus beta, y is equal to beta naught plus beta 1 x, then plus error time. So when we
you
are
are
writing
right.
the code, the error, which is the noise, was never taken care of. So what's the problem?
Fantastic. Okay, so but at the end of the day, you see that we see the residuals here. So you see in this LM function, okay, so LM function itself already has the formula, the data subset, the weight, the method, and then the model. You see, built in into this model is the error term. Okay, so it's a function. How do I describe a function now? Okay, so it's a code that has been written and the error term has been included in the whole code section. What I mean is if I take this whole thing and I copy it and I turn it to epsilon, I've already written several lines of code and I've captured everything and I now called it LM. So in the LM that we have here, this LM that we have, it has already captured the error term in it. So once you see the data, remember that we are using simulated data. So what you can see here is that we have our data, we have our parameters, okay, our variables, but with this LM captures beta naught, beta 1, beta 2, beta 3 plus the error term. So it is in this description. In short, this LM, I'll show you what LM is now. LM is, where is our material? That's a fantastic question. LM is this. LM. This is LM. Okay, so that LM that you wrote in front of that function already just picks all of this. Does that make sense, sir? You notice that in the code, we don't, in that specification, we don't have beta naught, we don't have beta 1, we don't have epsilon like you said, but it is, all of this is captured in that LM, in that linear model. That model itself already has that caption. Why we are not going too far into it is that you already know that we should start talking about the distribution of this epsilon, normally distributed, the errors are randomly independent and all of that. And you know, the issue of multicollinearity and independence, we are not even going there. Because what we are doing is we are just setting the foundation for us to understand how to implement linear regression. But at that level that you are talking about, that LM already captures the noise. I don't know if that satisfies you, sir. Which was a good break for me. That was a needed break. Okay. All right. So we are almost done. So we move to the second part of our discussion, which is hypothesis testing. Okay. And when you are testing hypothesis, you should also know that you need to specify the level of confidence that you have in the, you know, the specification. You must tell us. And the level of confidence is related to the amount of, you know, error that you are willing to commit. Back to error time again. So if I have a 95% level of confidence, I'm saying that I'm giving 5% of, you know, error. Okay, give or take at 0.05%, this is what will happen. So there are two hypotheses. There is the null hypothesis, which is the established theory. Okay, H naught is, or HA sometimes. Sorry, H naught, which is null hypothesis, is the established norm. That's what literature says. Literature says here that there's no relationship between independent variable and dependent variable. And you, the researcher, wants to say, I don't agree with that. Okay? You don't want to accept that claim. And that's why you go into research. So you come with your own hypothesis, which can be H1 or HA. Okay, so you are now saying that I don't agree that there's no relationship. I'm saying that at least one predictor significantly affects Y. You are not saying that it only affects, but that the effect is significant. In fact, this H naught is not also always saying that there is really no relationship, but it's saying that it's not significant enough. So it concludes and says there's no relationship. H naught is equal to no relationship. HA or H1 says there is a significant amount of relationship in at least one of the predictors because we are doing multiple linear regression. So where do we go? We want to also establish the confidence interval. How do we do that? Remember that we have already created our model. The first model that we created in today's work was titled model. Let's go and search for that. So the first one we did for linear regression was model, and we captured the summary. But by the time we had an extension, we now changed the name from model to model_MLR, which means multiple linear regression. And that was the summary that we saw last. Therefore, in this explanation of hypothesis testing and confidence interval, to be able to get the confidence interval, you need to use the conf_int function. And once you use a function, again, that function has a lot in it. Okay, it's like an algorithm that has been written and it has worked well and has been useful for, you know, getting the confidence interval irrespective of the data, so long as the relationship is what we are describing here. Then we specify, you know, our model and then give us a level of confidence. This can be 0.90, but 0.99, but in this case, is 0.95. When we run this, and we've run our initial code that we saw earlier, and we see that our p-value is less than 0.05 because our level of confidence is 0.95. That's why we are making a decision here. Our goal as a researcher, that is the vague goal that we have. We don't normally like the goal that after your research, you have not been able to, you know, disprove the H naught. researchers always want to. Some even do some, unethical things to make sure that this p-value is less than 0.05 if they are operating at 0.95 confidence level. So once your value is less than this alpha, then you will not accept H0. This thing says reject H0. Another fancy way of saying it is not accept H0, refuse to accept H0. So what you are saying is there is a significant relationship. That is, you are saying that age, for instance, affects, we have many variables now. In that example, we had age, experience, and education. So if you are taking age as the first, you can have 3 objectives. Maybe you want to see the effect of age, you want to see the interaction between age and education and their effect on salary. But here we are just saying that once your p-value is less than 0.05, which is what you desire, you can say that, yes, there's a significant relationship. But if it's otherwise, okay, you have to, so you have to fail to reject H0. Here you reject H0, yes. I was wrong what I said earlier. When p is less than 0.05, you reject H0. But when it is greater than, you fail to reject H0. Okay, so you stay with that situation. So what Dr. Debola was asking is also captured here. Okay, the issue of residuals. So residual refers to the difference between the real value and what you predicted. So if we go back to our linear equation, and then we have this line of best fit, it is possible that this line of best fit that you have drawn doesn't even have all the points on the line. The points might not be on the line. So if this is my point, this is what I predict. And then on this line is the actual value. The difference between my predicted value and my actual value is what we call residual. And once your residual is small, then you are predicting well. If it is large, then your prediction is not okay. So we'll go back to our, where are we now? What were we looking at? We're looking at our PowerPoint. Okay, good. So we go to our PowerPoint. And then we say here that difference between actual and predicted values are residual. Okay, so we now want to check the model assumption. Using a graph will really help us. So I'm going to now copy some lines of code again, and let's see how they show graphically. So once we were here, so let's go back to this code, and let's just copy it. When I say copy, let's replicate what's there. So we go here, and we want a graph. What do we want to plot? Our multiple linear, model, regression model. We want to pick just the residuals. So we pick the residuals and run that line. And then we have this graph, which we can zoom. I can make this bigger. So these are the residuals. Okay. You can see how distributed they are. There's so much of variance there. They are scattered everywhere. So this visualization can help. I hope you can see what I put on the screen. So that plot alone can help us. But we can go on and check the performance. This is evaluation now. Because it's not only for you to create a model, to use or train the model, you also need to find out how good is this model. Okay, so in trying to evaluate our model, we can use the R-squared value. What does the R-squared value do? It measures how well independent variables explain the variance in Y. So for the purpose of evaluation, I can come here and then put hashtag and say plot the residuals. So that when you are checking this, I said I was going to send you this file, okay? So I will now put hashtag. I can say evaluating performance or evaluation if I like. Okay. So what do we have there? We want to get the R-squared. What we do with R squared is that we get our summary statistics. Inside that summary statistics, we are checking for the summary of our multiple linear regression model. And then we are now picking the R squared. That's the metric that we are using for evaluation. That's not the only one that you can use for evaluation. For instance, we are still going to see the root mean squared error. Okay, so let's run that. And then we have 0.005693, which is not impressive because you expect this to be, we'll talk about that as we go on. But let's compare that with the root mean square. So in the case of the root mean square, because it has a lot of mathematics involved in it, you look for the square root, you look for the mean, and you look for the square in reverse order. That means you square the residuals, find their average, which is mean, and then the square root. So if we call that RMSE, which is root mean square, okay, there is actually a root mean square function, but let's just go on. We say that at the outer level, what we are calculating is the square root, but we need the square root of the mean values. And what mean values are we looking at? We are looking at the square of the residuals. Root, square root, mean of what? Squared. Root means square. What are you squaring? The residual. The residual from where? From our multiple linear regression model. What are we capturing? We are capturing the residuals. I'm doing this today this way because it's my desire that you also just follow, just follow and code. When you watch the video, you can slow it down and make sure you code these things. That's where the difference lies. The difference lies in actual coding. Remember that we say it's root mean square. So it's not just the residual, but the square of the residual. So we use the caret symbol and then we'll put 2 there. So don't forget, you get the residuals from the model, you square the residuals, you find the mean, and then the square root of the mean. So if I run that line of code, I would have captured RMSE. So if I go to the next line and say print RMSE for me, I'll have print bracket root mean squared error. If I run that, I have this value 25517.63. In our next class, which is important, or subsequent classes, because we'll keep, whenever we do predictions, we'll keep evaluating our prediction. Then we'll slow down and explain some of the meanings of these results. Where are we now? So we go on, and then you have your practical exercise. I'm going to copy this practical exercise. I'll take it to the classroom. I'll paste it there. Where are we now? I don't even know where I am again. Where are we watching? Where is our okay, we are using this. So I'll go to our charts and then I'll paste that there. So please, I beg of you, okay, it's an appeal from me that you just try to do this, First, fit a simple and multiple linear regression model. You can get data from your department. Maybe you have the grades, maybe you can use whatever, maybe salary scale, whatever. Just use data and try to demonstrate this. If you need help, let me know. You can contact me. Then when you now get your result, try to see if you can interpret the results and then see if you can visualize using ggplot and then perform hypothesis testing. So what are the key takeaways from today's lecture? Number one, we're able to fit a simple linear regression model where we use age and salary. We also fitted a multiple linear regression and extension of the simple one where we added 2 more variables, which are education and experience. Then we looked at initial interpretation of the coefficient, p-values, and R squared. We'll look at it in more details. we talked about visualizing regression results using ggplot2, which we, is a fallout of what we did last week. It's just like trying to reinforce last week's learning. Then we did a bit of performing hypothesis testing and residual analysis. This is what we have for today. Initially, I thought that I'll be sending this to, I'll be giving you another demonstration, which maybe, let me just try something. Let's see, we still have some time. Do I have this here? I'm coming, just a moment. Okay, I can't find that file. Okay, let's see this file. Let's see whether it's the same file. Okay, good. So maybe what I will do is, let me just run through this, and then I will send this one to you. Instead of sending the new one we did today, I'll send this one to you because this one contains some of the notes. I'll even send both of them. Okay, I'll send both of them, but let me just show you. Here, the library that we are using are ggplot2 and the, mass library. Okay, if you want to know what the mass library is, it's just a mathematical or statistical library. So we say mass, and then we check. We can say mass library. Okay. Okay, let's just say mass library in R. So he says that, let's go there. I don't like this. Modern applied statistics with S. Okay, so it's a library. And this takes me back to what I was trying to tell Dr. Ademola, that somebody has already built this mass library and you just call it. You can see that we have functions here already. So you already have those things already programmed into the library. Okay, so that's why we were not doing those specification of LM and all of that. So these are the two libraries that you need. If I run this line and the next line, here I'm setting seed. I want to create artificial data, okay, simulated. In my own example too, I'm predicting salary using age and experience. But now, my own values are, a random selection from a normal distribution with mean 15. That's experience. But for age, I want the mean to be 40 and standard deviation to be 10. Don't worry, as we go by and by, you understand how to specify this yourself. So yeah, these are the outputs for the, simulated values. So we have experience, we have salary, we now create a data set that has everything. And when we print our data set, we are going to have a data frame, okay, which will have several columns, and the columns will be things like age, experience, and all of that. So you can see again, the model specification is still salary against age and experience, this multiple regression. Then data is data, not DF in this example. So if I run this code and I get the summary statistics, we'll have this result. And once you check here, you will see that experience is significant. Age is also significant. I told you about using this as a guide. If you go on, I can now do a diagnosis of the residuals beyond what we did before. So let me try to clean this so that you can see the output that I'm going to generate. So first, if I run this, okay, what this does for me is that it creates like a grid. Okay, it creates a grid so that an environment is created. But if I now plot my model that I created there, then I'm going to have this output where you see residuals against fitted. You can make this to be, bigger, and then you can see the QQ residual plot. Some of these things, we might look at them, but just to show you that in terms of demonstration, there is still much that we could do, okay, building on the foundational lecture. This one, not simulated data. This is now real data, okay, secondary data, the Boston housing data set. So what do? We load this package, the mass package. The Boston data set is in R, Okay, so we can get data sets that are already in R. We can actually import data sets from externally. For instance, if we want to import data set and we come here, I hope you can see my cursor. You will see that there are different types of data that we can import. There's Excel data, there's SPSS, there's SAS, there's Stata, and so on. But this one is data that is inside the R Studio. So when I run that and I print the posting data set, you are going to have these features here. Okay, we have features like, I think this is the rate of crime. This could be maybe zone, maybe, I don't know, the number of rooms, the age of the house, and some other, characteristics. If you want to read more about the Boston data set, a simple Google search will help you. If I go online and I open a new tab and I say the dictionary of the Boston housing price data set, just this search can give me the result. So if I go to this link, Kaggle, I'm going to see the features, full description of the features. Well, this is beautiful that I was able to get to this place so that you can see that even the first thing I mentioned, I was not even correct. So, okay, to a large extent. So, per capita crime rate by town. ZN, proportion of residential land zone for lots over 25,000 square feet. Portion of non-retailable business, and so on. And so this one gives us a description of the data set. To help you, I can copy this, put it in the chart so that I can go there and explore, that data set, and then, even check the code that is used there. There's a lot I can learn. If you need to sign up on Kaggle, that would be nice, because there's hardly any major data scientist who is not on Kaggle. I mean, on the average. That's not to say that if you are not on it, then you are nowhere. No. We're just saying a lot of data scientists are there. It's a beautiful platform, not just for learning. No. And what was I? Okay, I was running code. So I'll go back to my R. So we have our Boston data set. Okay, we created our model, and then we are using linear model. Our dependent variable is this MEDF. Whatever it means, you check there. And we are only considering 3 columns. The name of our data set is Boston. So as I get to the end of the class, I will just run this code and then, see some visualizations here. Thank you very much for listening. It's a good thing that we have our code already, recorded. We have these things recorded, so I can save this as, or better still, I can download it. So what I'm going to do is I'm going to download this and put it in the chat, the 2 files, the one that we used in class and this one that I built myself to help us reinforce the learning. Thank you very much. I don't know if we can get responses. Thank you very much, everyone.
Thank you, sir, for the lecture. Hello, are you with me?
Yes, sir, I can hear you.
Yeah, please, I want us to go back to the lecture notes. There is a particular place I'm not too clear, especially on that P value, under the test of hypothesis.
Fantastic. So we go, good. Can you imagine? I've closed that document. So let me reopen it. So if I come here.
Actually, I don't want to interrupt you. That's why we
No, don't worry. It's good. That's where learning comes in, because sometimes one could say something that is incorrect, and this thing is being recorded. So it's okay. So we're talking about p-value, right?
Yeah, under the test of hypothesis.
Yeah.
Where you have H2 and H1.
Am I sharing my?
Not at all.
Oh, sorry. I've been trying to, okay, so entire screen. Can you see my screen now?
Yeah.
Are you talking about here or in the code?
Yes, the p-value interpretation.
Yeah.
I'm looking at when p is less than 0.05. You
Yes.
say we should reject HO.
Yes.
And that
So
means that
yes. Very good
significant
question.
relationship. But
Yes,
in
excellent.
our HO, in the null hypothesis,
Yes.
we have
Yes, go
HO
on.
to be no relationship
Yes.
between the variables and the dependent
Yes.
variables. So
Yes.
when we are rejecting it, automatically we are accepting HA.
Fantastic. So
Okay,
just to confirm, HO says no relationship. We reject HO, we say there's relationship.
Okay.
When do we do that? First, we set a significant level, 95, which means we only have a permission of 0.05.
That's true.
So we want it to be less than 0.05 because we are the researcher. We are the one coming with an argument. You've spent 6 months writing a research, and you want to say that if you give people a Christmas bonus, it will affect their performance in the following year. That's what you are proposing. But the status quo says no, Christmas bonus does not affect anything. So maybe there is literature. The literature says they found out that Christmas bonus does not affect. But you are coming with a research that now in Nigeria, using Nigeria as case study, Christmas bonus will affect. I say, okay, so what level are you confident? I'm 95% confident. Okay, let's analyze. And now we have analyzed. Now our rule now is if at the end of the day, our p-value is less than 0.5, then you have won the argument. So when you win the argument, you reject H0. When you lose, you sustain H0. That is, it doesn't affect. There's no relationship. Make sense?
Okay, yeah.
All right.
Clear.
Okay. Thank you, everybody. We'll see you next week. God bless you.